Okay, let's look at a 10 megahertz GPS frequency standard. The design uses a U-Blox Neo 7M GPS. It's built onto a QT-PY49 card. The processor is on a QT-PY49 card. The processor is either a SAM21D processor or an RP2040 processor. The code size is small enough to fit into a SAMD part. Here's the parts in an enclosure. Let's look at each of the individual pieces that make up the design. The first piece is the QT-PY49 card. It's a LAN boards card. It mounts the processor to it. The next card is a modified pulse gen card. It's used as a 50 ohm driver. It takes in the pulse per second signal from the GPS, which gets changed to whatever frequency you want to set it to, in this case 10 megahertz. It's powered off 3.3 volts. The 3.3 volts comes from the QT-PY49 card. The processor is either a SAM21D part or an RP2040 part. The RP2040 is the same processor used in the Raspberry Pi Pico. The SAMD21 has limited code space, but the design will fit inside of the SAMD21. The card is running Circuit Python. There's a lock LED that blinks on for a second when the power comes on, then blinks while packets are waiting to get received intermittently. Blink, blink, blink. And once there's a lock, it comes on and stays on solidly. The LED can be seen through the front panel. The GPS is a U-Blox Neo 7M part. The enclosure is a standard 100 by 76 by 35 millimeter extruded aluminum enclosure. The cards are fastened down with 440 screws and nuts. The cabling between the cards is DuPont ribbon cable style cables. Here's a view from one of the sides of the enclosure. The connector in the middle of the box is the USB-C that is on the QT-Py card. It's used for power or for programming, but it's not necessary to run the frequency standard. The card itself is autonomous. The lock LED is also shown. I picked a green LED, but any color would work. It's connected up to one of the digital pins on the QT-Py processor card. Here's a view of the other side of the box. On the left is the external GPS antenna. I have it several feet outside my window, attached sitting on a fence. It's a magnetic mount antenna. The other connector is BNC, and it outputs 10 megahertz with a 50 ohm drive. The 50 ohm drive is provided by the Pulse Gen card. The labels are P-Touch labels, white on black. I like big labels to make things easy to read. The pictures, most of the pictures were taken before the cables were dressed in with zip ties. The wiring in the cables are color coded. Red for power, 3.3 volts. Black for ground. Let's take a look at the Circuit Python code for the card. It's pretty simple. It's not using GPS code. It's using just serial UART code to talk to the, or to listen and talk to the GPS. I've got a wiki page that describes the build, and I'll put a link down in the show notes to the wiki page. There's a picture. We've already looked at the architecture of the card, pieces of the card, and there's a link here to the Circuit Python code. As I mentioned, it runs either in a SAMD part, which is either made by Seed Studio or by Adafruit. The one I'm using is Adafruit, or a QT-Py RP40, which is again either the XIAO part by Seed Studio or the Adafruit part, and that's 40 megahertz or 48, not really sure, 3.3 volts processor. The Pulse Gen card mentioned in the status light, and that's a picture showing the picture shows the aluminum box. The design is inspired by the Skullcom design. That's kind of what got me started here. His design is very well documented. He's got a nice set of videos, little keypad, and he's using an Arduino Nano to control it. He can set frequencies. I just want a fixed frequency, but I put in some capabilities to have different frequencies. I've just got one at the moment, because that's really all I want is a good 10 megahertz 50 ohm source for my lab. His software, he's got a piece of software up there that runs in the Arduino, and I use that piece of software modified to generate the byte string values that need to be sent out to the part, to the GPS. So let's take a quick look at the code. It's also, as I said, linked. And here's the code. The code is currently called GPS _004.python. And when you go to run it, if you want it to auto run, you have to save it on the device itself, the Circuit Python device, as code.py, and it'll run automatically when the power gets turned on. It does communicate with the module. There is a capability in another version of the code to read and print the serial data. That's currently not being done in this version. I like to always put a wiring table in to show the colors of the wires for me to keep track of how the wiring is set up. There's the serial, the power and ground go to the GPS and go to the pulse gen, and then this is serial transmit and receive. And because it's always confusing to me to call one side transmit and one side receive, and keeping track of which is which, I just call it from the QT byte to the GPS. So it's this particular connection is transmit out of the QTPY to the into the receive of the GPS, and vice versa. And the pulse per second gets wired over the pulse gen to a pin where the oscillator normally would be. Now I did run it with the capture and grab some screens just so I'd have an idea of what the data looks like out of the GPS. And there's one particular message we're looking for. It's this GPGGA message, and it comes up with variable lengths depending upon when the thing starts up. In this particular case, really all we really care about is the number of satellites, and that's over here in this position. So at this particular point of capture, it's come up with 7 satellites. Fairly straightforward set of normal imports. I do want the digital in and out for the LED control. Time isn't totally necessary. I've used it. Was having some issues with garbage collection in an earlier version of it, so I put in the GC function as well. It's not currently being used. To talk to the UART, you just call the bus IO UART with the transmit receive pins, and UARTs are always 9600 baud. They spew out a lot of data, so you kind of have to have something that's capable of keeping up with that data. Here's that magic byte string. This particular sequence is for 10 megahertz, but I also generated it for 8 megahertz and 1 megahertz. And this string was generated by taking the Skullcom code, and instead of talking to a GPS, just dumping it to the screen and then capturing it. That was helpful as well. The link to do that is up here in the code. Maybe it's farther down. Anyway, did have a free, at some point I had a lot of print messages to try to help me debug, but I turned them all off because I don't need them once I'm running. Frequency set flag is used to tell whether the frequency's been set for changing the light from blinking to solid on. The LED gets set up. I guess I do use time to sleep for a second because I want to leave the light on for 1 second when it comes on so that I know that I'm powered up properly. Serial byte string is empty. That's the string that the characters are going to be received from the device in. I'm only reading one character at a time here, and blinking the light every 50 characters that are received. So it's toggling that LED value and resetting the count back. So it increments up a count of 1 every potential character. If the serial value is not none, meaning it received a character, it's going to append that value into the serial byte string, which we created up earlier. If there's an end of line character, then it will take and convert that string from a byte string into a regular string. Look in that string and see if that GPGGA is inside of that string. And when you've started receiving, the string can be shorter. So I make sure the string is long enough, and I make sure that the 45th offset from 0 and the 48th offset from 0 both have a comma in it. Then I know I've got a legitimate string. And between that, at locations 46 and 47 is that number of satellites flagged from earlier. I grab that, turn it into an integer. If it's 0, I set it to false for frequency set. If it's not yet set and the number of satellites is greater than 0, then I write out to the UART that byte string that was calculated from the Skullcom code, set the freq set flag, and set the LED on solid. So that's really all there is to it, and then clear off that byte string. So the code is not that complicated to run. It's making this byte string that was a little bit of work, but it could be generated by looking at the data sheet, and I had to look at the data sheet to make sure the values were correct. The slightly painful part is just the checksum out at the end of the line, and I really just didn't want to deal with that checksum, because if you notice, the checksums are different for the 3 different frequencies. I wanted to make it a little bit simpler. Yeah, again, 10 megahertz, 8 megahertz, or 1 megahertz. I could probably put a switch on here or do something to affect that. Again, keeping it simple at this point. I don't think there's enough code space inside of the SAM version of the part to put a display and such on it. If I use the RP 2040 version, I could certainly run an OLED display and have a knob and change the frequency, things like that. But that's pretty much all there is to the code. Pretty straightforward. And let's put the USB cable in. See, the light comes on for a second and then blinks intermittently until a lock comes. I won't wait around for it. It takes some period of time depending upon how much stuff, how long it's been off, and how hard it is to find the satellites and that sort of thing. But eventually it comes on solid. And here's the device after it is in lock. And you can see it's 10 megahertz. This counter's off by a digit. Got a couple of different counters sitting around here, but pretty good. If you want more information, you can see our wiki pages for these products, and we have YouTube videos on them as well. We have a store in Tindy where we sell all of our cards. Thanks for watching our video, and if you enjoyed it, don't forget to like, share, and subscribe.